So in the previous chapter, I talked about sampling. Like if you wanted to collect data on on a certain population, you take smaller samples, hopefully by some sort of randomization if you want to avoid bias. This section is about experiments when you want to look at the relationship between variables and see if you can show causation is the ultimate goal of an experiment usually. So first of all, I want to point out the difference between an observational study and an experiment. Now you can see observational studies that are set up with control groups and everything, and they sound, or they're at least divided into groups, and they sound a lot like an experiment, but the difference is an experiment has a treatment. Okay? You deliberately impose some treatment on the individuals. Observational studies, you're just collecting the data. You may divide the people into groups or something, but you didn't manipulate in any way. You didn't do a treatment to influence the data. Okay? So when your goal is to understand cause and effect, experiments are the only source of fully convincing data if you can do randomized experiments. Okay, some terminology here: individuals, factors, and treatments. So the purpose of an experiment is typically to investigate the relationship between two variables. Just like when we looked at linear regression, you have your explanatory variable and your response variable. If you think that the first variable causes some sort of output in the other variable, then we call the input variable, the explanatory variable, the output variable, the response variable. The different values of the explanatory variable are called treatments, and an experimental unit is the single object or individual that is to be measured. Some things to look out for, and again, we talked about these a little bit, very closely related when we talked about correlation. Lurking variables and confounding is a term that goes along with lurking variables. So you have a couple of variables you're interested in, but they're related to one or more other variables. Those variables in the background are called the lurking variables, and they can influence the relationship. And as it says here, confounding occurs when two variables are associated in a way that the effects on the response variable cannot be distinguished from each other. Okay, so you don't know what's actually causing which variable is causing the response. So well-designed experiments take steps to avoid confounding by using randomization. Okay? So here's an example of one that is not a well-designed experiment, but is common to see in real life because a lot of times we collect data in the only way that we can. But a high school regularly offers a review course to prepare students for the SAT. This year, budget cuts will allow the school to offer only an online version of the course. So you have the students taking the online course and we have their SAT scores. Over the past 10 years, the average SAT score of students in the classroom course was 1620. The online group gets an average score of 1780. That's roughly 10% higher than the long-time average for those who took the classroom review course. Is the online course more effective? Well, the point is, maybe, maybe not. We don't know. Okay? There could be lots of lurking variables. We can't convincingly make that conclusion because of the possibility of lurking variables. And I said, for example, maybe there's all new teachers this year. And these teachers are just more effective than the teachers were in the past. Who knows? There's a lot of potential lurking variables. Maybe the students who took the online course, when a lot of these problems were written is when technology was first starting to boom with the internet, and people with more income had easier access to the technology. And it's still the case that a lot of people with more income have access to better technology than people with smaller incomes. So there could be all sorts of lurking variables at play there. We just don't know. It says it would be better if you had a control group and a treatment group from the same population somehow. So what you want to do is some sort of randomized experiment, just like with sampling. If you can randomize, you can, in theory, kind of evenly spread out the lurking variables. Okay? So we can avoid bias if we can do random assignment. And you can read through that in the notes there, but I'm going to skip ahead to the picture here that kind of gives you the idea. So you have your experimental units that you're going to get data on, which could be people, okay, but not necessarily. But you're going to do some sort of random assignment and split them into some number of groups. It could be more than two groups. It's pretty common to have a control group and a treatment group that we call them. And then you do some sort of treatment, which could be your control group that receives like the normal treatment. Like maybe it's a new classroom teaching method, and you have your traditional classroom, and then you have the novel new teaching method, okay, the flipped classroom or something. And then you compare the results at the end. Okay? So you randomly assign to the groups so that if there are lurking variables, the people with certain qualities of those lurking variables are equally likely to get spread out between the two groups or however many groups you have. then you can more likely contribute to the treatment, whatever's happening with the results. So the idea, you're controlling for the lurking variables, okay, splitting them out between the groups, using randomization to do that, use chance to assign experimental units to treatments, and also replication. If you can do it over and over and get similar results, you have stronger evidence. When we get to inferential statistics, we'll use the term statistically significant. Okay, we'll make judgments based on probability of whether or not we have convincing evidence. And says statistical significance associated with data from a well-designed experiment does imply causation. Okay. So cautions about experimentation. There's lots of ways to bias experiments. There's lots of examples you can read from psychology and different areas, but I think of psychology definitely where you're looking at the way people think and the way they act, and what you think about that may have some influence on that. We even have what's called the placebo effect in medicine, where thinking that a drug is going to help you, like say it's a drug supposed to help you with depression, if you think it's going to help, it probably will help. It's more likely to help. There's evidence of the placebo effect. So ways you can avoid that is use what's called blinding. I just have the definition here of double blinding, but blind is where the people receiving the treatment don't know which treatment they're receiving. For instance, some people are getting medicine and some people are getting a placebo, which is a sugar pill that looks like the medicine. Double blind is when the people collecting the information don't know either. Somebody has to know, have the master list to match it up, but maybe a professor hires a graduate student that collects the data and the professor is then able to match it up. Because sometimes when you're even the researcher, they're looking for certain things which could bias the results. So double blind, they don't know, who has certain qualities. So doing a blind or double blind is a way to add to the confidence of the study. There's a thing called block designs, which is kind of similar to stratified sampling, but for experiments. So you develop blocks or these different groups, such as male, female. There's some sort of characteristic you want to split the groups by before you do random sampling, and then you do random sampling within the blocks. Okay? It says control what you can, block on what you can't, and randomize to create comparable groups. Here's a picture, an example of that. So again, we're looking at something, I don't know what's being studied here, but we're going to do some sort of randomized experiment, and maybe we have 3 different treatments, but maybe it's a physical, some sort of medical experiment or something, and men and women are very different biologically, so maybe the drug is going to affect them in different ways or something. So we're going to split men and women separately and then do random sampling within each of those. Basically, you're going to conduct the experiment within the different blocks. So that's what blocking is. A blocked sample, a blocked experiment is when you develop these blocks, these different characteristics, different groups, very similar to the strata when we did sampling. And then within each of the groups, you do the random experiment. And then the last thing is matched pairs design is a very common one. Matched pairs design, probably the most common way is you see the same individuals receive the different treatments and then you can match them up. So you pair up individuals that are similar in some way that receive the different treatments and then compare the results. There's examples of like medical experiments that use identical twins as one way to do it without having the same people, because there's always difficulty when you have the same people doing the same thing different times, but it is very common to do like a pre-test and a post-test and do a matched pairs design where you have the same individuals doing something, receiving a treatment, and then you have the end results. So matched pairs is when you have your groups can be matched up. Okay. And that is it for this short section.